All right, in the last lecture we talked about the difference between random and systematic error. So in today's lecture we're going to be talking a lot about random error, specifically related to Gaussian random distributions, standard deviations, then we're going to be talking about uncertainty and confidence intervals, and finally we're going to talk about the real rule about significant figures. Okay, so to illustrate this idea of random error, we talked about random error already. Let's talk about the Galileo ball drop experiment. So many of you are probably familiar with this experiment where Galileo supposedly stood on the Leaning Tower of Pisa and dropped two balls of different weights, and he showed that those balls land at the same time, even though they have different sizes. Okay, so I wanted to use this example as an illustration of random error. So, for example, if I had a stopwatch and I was measuring how long it took for each of these balls to drop, and I measured it several different times, each time I measured that drop, I might hit the stopwatch a little bit too early or just slightly too late, and there'd be just a little bit of variation back and forth. There'd be some random error. And so this is exactly what I did. I actually found a virtual experiment for the Galileo ball drop. You guys can go, here to this website and check it out if you are interested. And it's a virtual experiment, so it shows Galileo dropping, well, cartoon Galileo dropping the balls. And I literally took a stopwatch and just measured how long it took for the balls to drop. And I did this 20 times. Okay, and I plotted the times that I measured and the frequencies in this plot. So let's introduce this idea of a Gaussian distribution. So a Gaussian distribution is often called a normal distribution, and it describes the distribution of random error. And if an experiment is repeated a lot, so approaching infinity, or even doesn't have to be close to infinity, it could even just be a large number like 1,000 times. And if you only have random error, remember this concept of random error, then the results will tend to cluster symmetrically about the average value. And when this happens, we call this ideal smooth curve that's a result a Gaussian distribution. We use this equation to plot a Gaussian distribution. So this mu is our average value if we have an infinite number of measurements. So this is average. And this sigma is our standard deviation if we have an infinite number of measurements. So we'll do this in class where we'll have you guys practice plotting a Gaussian distribution. So again, these blue lines were my measurements, and you can see that I probably had maybe even had some systematic error associated with this. But if I kept, I only did this 20 times, but if I kept measuring the time that it took for these balls to drop, hopefully it would approach a more Gaussian distribution. Okay, so just to remind you, this so here we use mu to describe our average, but if we only have a certain number of data points, so my 20 data points, we use x bar to label average, our sample mean, because we have a finite sample. And again, all this is the sum of the individual measurements divided by the total number of measurements. So right here, this is going to be our x bar. It's going to be somewhere right there. Or for this Gaussian curve, that's going to be equal. This Gaussian curve is assuming an infinite number of measurements, so that will be equal to our mu, our hypothetical average. Okay, so next we need to talk about standard deviation. So standard deviation is a term that's used quite a bit with normal or Gaussian distributions. Standard deviation is a very simple idea. It's just quantifying the amount of variation for a given measurement, set of measurements. So this is our formula for standard deviation. And you can see all it is you take the difference between each data point and the sample average. So that gives you this variation from the average. And what we do is we square those differences, sum them all up, and then take the square root. And the reason why we do this is if we square it and then take the square root, then that will give us an absolute value of the variation rather than the absolute value. So if we have some values that are higher than the average or some values that are lower than the average, this formula won't care what direction that variation is. And then we divide it by n minus 1, and we call this our degrees of freedom. And we'll talk more about that when we get to confidence intervals. And remember that we learned about precision and accuracy last time. It's important to remember that the closer your standard deviation is to 0, the more precise your set of data. But if we're going to report the time that it took for the ball to drop, we would want to report the uncertainty. So how certain we are that the measured value is the quote-unquote true value. So there's two different types of uncertainty. The first is the standard uncertainty, and the standard uncertainty is the mean of the uncertainty of the average. But to calculate the standard uncertainty, you have to know the quote-unquote true population standard deviation, sigma, and you divide that by the number of measurements, which is n. The problem is that it's most likely you don't know the true population standard deviation. So if you have a smaller data set, which you pretty much always will have, then the uncertainty that we will actually use this calculation to report our confidence interval, where this value, t times s divided by the square root of n, is our uncertainty for a limited number of measurements, because for a limited number of measurements we won't know the true population mean or the true population standard deviation. What we do know is the sample average, which we call x bar, and the sample standard deviation, which we call s. So we'll use this equation to be able to report how certain we are about a specific measurement. So this s is the standard deviation, n is the number of measurements, and this t value is the student's t. It's just a statistical tool that's used frequently to express confidence intervals and to compare results from different experiments. So it might help you to print off or to keep a copy of t values. And basically, you have different t values for different levels of confidence. So you can see that for a given uncertainty, if we have some measured standard deviation and some number of measurements, let's say we have 5 measurements. Well, we need to look up the t value. To look up the t value, we need to know our degrees of freedom. And our degrees of freedom is just equal to n minus 1. So it's your number of measurements minus 1. So let's say for that ball drop example, let's say that we only did 5 measurements. So that means that our degrees of freedom, which here is just labeled df, would just be 4. 5 minus 1 is 4. And let's say we wanted a 95% confidence interval. That's going to be the most typical confidence level that you'll see reported, that I've seen at least in my experience. So you'll go and you'll say, okay, I've got 4 degrees of freedom. I want a 95% confidence interval. So this will be my t value, 2.776. Harris on page 71, it gives you the definition of a confidence interval. And it just says the meaning of a confidence interval is this: if we were to repeat the n measurements many times to compute the mean and standard deviation, the 95% confidence interval would include the true population mean in 95% of the sets of n measurements. So this is kind of a complicated definition. We have a little bit more imprecise definition that's a little bit simpler. It says if you have this 95% confidence level, then you can just say that you're 95% confident that the true mean lies within that confidence interval. Okay, so again, we use this confidence interval or uncertainty to describe how confident we are about a specific measurement. And an important thing when you're reporting an average and it's associated in uncertainty is you want to be really careful about significant figures. So we call this the real rule of significant figures, and that's just that the first digit of uncertainty is the last significant digit in your reported measurement. If we had some mass that we weighed several times and we got that the average mass, let's say that we weighed it 6 times, we got that our average mass was equal to 5.0356 grams. If we then calculated the confidence interval, so let's say that we calculated the confidence interval to be plus or minus 0.1 grams, then this first digit in our confidence interval would be our last digit that we would report in our average value. So we would say that our mass is 5.0 plus or minus 0.1 grams. And that's how you would report it. And this, again, is really important because anytime you report a measurement, you need to be able to understand the uncertainty associated with that measurement, because otherwise this measurement is not as meaningful. Okay, going back to our example of the ball drop, we can, because we know the standard deviation and we know the t-value we can look up, we can calculate the confidence interval. So our uncertainty, our confidence interval is going to be plus or minus the t-value times our standard deviation divided by the square root of n. The t-value, if you look it up in a table with 19 degrees of freedom and a 95% confidence interval, is 2.09. And our standard deviation is 0.15. And we divide that by the square root of number of data points, which in this case is 20. And if you calculate this out, you'll get plus or minus 0.07. Okay, so now when we go to report our average time that it took to drop the ball, we'll say that our time was 2.70 plus or minus 0.07 seconds. So we want to include the hundredths place because that's the first digit of our uncertainty. And that would be how we would report this value.